So, did we go over the answers to this?
Yeah.
I think we did.
Yes.
Yeah, so basically all the assumptions were, or all the conclusions were the same. No big surprise, again, because you know, none of our assumptions were violated. Our normality assumption, everything was normally distributed. So, you know, our t-test and our assigned test should come up with similar answers. The only exception would be if our t-test comes up with a p-value around like 0.04, right near that 0.05 level. Our t-test would be significant. We'd reject the claim that our means are equal, but then our sign test might actually be, might give a p-value of like 0.06, where we'd fail to reject it, and that's just due to the difference in the power. Once we convert to plus and minuses, we lost the information about the actual numbers, and once we lose that information, we lose power. All right, bootstrapping. So that was a sign test, but oftentimes we don't want to compare the medians. We are still interested in comparing the means. How do we get around that? Well, we could run a bootstrap t-test. It's a little bit more, a little bit harder, right, because we have to ensure that our null hypothesis is actually true when we generate our null distribution. Right? Or we can do bootstrap confidence intervals. Now, this is all review. We've already done it. We've already made our bootstrap confidence intervals. So I give general R code to do it, but not only that, but I also posted, we had the sign test, on Blackboard I posted a bootstrapped confidence interval function. So if you go to the functions, this, so we go to our functions, we will see that we have a bootstrap confidence interval. When I click on this, I'm going to open this up in R. That over. Here's our function. So bootstrap confidence interval function. So again, this is, we were doing bootstrapping, doing it manually, right? We basically had a script where we would replace a single value, and that can work. But I like doing the function because the function then can then be passed to our aggregate function, and the aggregate function will calculate group means and group variances for us. We don't have to go by and select our individual groups. So here's our function. You're going to see a lot of the same things that we have that were in that original script. So we have na.omit, so that kind of strips out all our missing data. We have our loop to calculate all of our bootstrap means. And then we have our quantile function that'll calculate our confidence interval, right? Everything that we've done or that we learned about. But now what I've done is created the function so that we can specify how many bootstrap replicates we want. So we can specify our n, which is the number of iterations. And I also have it to where we can specify our confidence interval, so we don't have to worry about figuring out what quantiles do we use. This function will do it for us. So how do we use it? Well, we have the function. I'm going to copy this, copy the entire function, and I'm going to go back to our markdown document. And I have this spot for the functions. So I'm going to create a bootstrapped confidence function chunk, and I'm going to paste that in there. And now when I run it, you'll see that we have bs.mean appears. Let me load this up. So now our bootstrapped bs.mean function now appears. How do we use it? Well, I'm going to go down here. So this was a sign test. That was a sign test. So we are on bootstrapped confidence intervals. All right, so bootstrap confidence intervals. Let's kind of set this up and then give examples on how we would use it. Why did the screen go black? Must be an issue with our graphics card. All right, so bootstrap confidence intervals. When would we use it? We would use these when we violate normality and we want to compare our sample mean to a hypothesized mean. And just in parentheses, I'm going to add a note. Sign test compares medians. All right. So we don't really want to switch to sign test because we don't want to compare medians. We are interested in comparing our actual sample means. That's our focus. All right. Compare our sample mean to our hypothesized mean. All right. How do we use the confidence interval? Confidence interval function. So what we're going to do is just generate. We already generated a data set. I'm going to go back to this data set that we generated and used for the sign test. So this was DAT1 is what I called it. Okay, so we'll use DAT1 in this example. All right, so for a 95% confidence interval, Ci with 10,000 replicates, we use bs.mean. All right, that's our function. We already loaded the function, so it's in memory. So we will use our vector, which is dat1. We're going to specify n is 10,000. That's how many iterations we're going to use. And our confidence interval, the default is 95%. We're going to keep it at 95%. This percent has to be reported as a decimal. And when I run this, it will fairly quickly give us a confidence interval. So we're going to use bs.mean, our x, n, and ci. X is our numeric vector. N is number of iterations or bootstrapped replicates. And Ci is the confidence interval as a decimal. So kind of laid out how we use it. So for our bootstrapped confidence interval of this dat1, this is what we get. Interpretation. Our sample mean is equal to any value, any hypothesized, mean that is captured by the bootstrapped Ci. All right, and this is at the alpha equal 5% level. So alpha equals 5% corresponds to that 95% confidence interval. So for this example, our sample mean is equal to all hypothesized means that hypothesized mean from 6.9 up to 10.4. And we include the values. So if I asked, is our sample mean equal to 7? 7 is captured by our bootstrapped confidence interval. We would conclude that our sample mean is equal to 7. If I ask, is our sample mean equal to 8.5? 8.5 is captured by our confidence interval, so we would conclude that our sample mean is equal to 8.5. If we ask, is our sample mean equal to 11? 11 is not captured by our confidence interval, therefore we would conclude that our sample mean is not equal to 11. So our sample mean is equal to any hypothesized mean that is captured by the bootstrapped confidence interval. If the confidence interval does not capture the hypothesized mean, then our sample mean is not equal to that hypothesized mean. Not too bad. BS.mean function is really useful. If we wanted to change our alpha level to, let's say, 1%, and we wanted a 99% confidence interval, all I have to do is change that CI, and our function will automatically change that. So you can see at 99% confidence interval, it gets larger. Hey, it gets, what is it? It gets smaller? 99? No, it gets larger. So we want to be 99% confident that we capture, so it's going to get larger. 95% gets smaller. If we do a 50% confidence, we're getting a much narrower, much smaller range. But that's the great thing about this bootstrap confidence intervals. What if we only wanted to do 10 replicates? I don't know why you'd want to do it, but this is how we would do it. We just change it. Now, the default is 1,000 because if you have something like a really large vector, it's bootstrapping. It's taking a random sample the same size as that vector. So if you have, a vector of 500 data points, doing 10,000 replicates will actually happen pretty quickly. But instead of 500 data points, let's say you have 5 million data points. Now our bootstrap sample is going to probably take a long time to do. So I kind of set it at 1,000 to try to reduce the chance that you're going to run one of these things and it's just going to sit there because it calculates for a long time. I've never done like a massive sample size like that. All right, so we have our bootstrap confidence intervals. I have our interpretation. All right, bootstrap sample mean is equal, or the sample mean is equal to all hypothesized values that are within our confidence interval, and the sample mean is not equal to any value that is not captured by our range. This works. When we do t-test, this is going to give us the same answers. All right. It's actually better when we violate than a t-test when we violate normality, because again, when we violate normality, we no longer follow that t-distribution. I actually prefer the confidence interval over the sign test because we're normally comparing means. That's what we're interested in. And it's really easy to calculate. BS.mean function. That works. Problem, though, is that there's no p-value associated with it. And again, some people really need to see a p-value. So if you have to have a p-value, do a sign test or come talk to me and we can do a bootstrap t-test. So I did this. This was for Pond 1. Right, this was kind of how we did it long way. This was using our function, but I gave you the bootstrap mean function. It's right here. All right, and I posted it as an R script. When you do this, when I did it, I captured this. So let's go ahead and do bootstrap confidence interval for pond 1. Remember that first question was, is our sample mean equal to 24.5? We met all of our assumptions. T-test works, but let's try it for our ponds. All right, so go ahead, do pond 1. So I had that. When I ran it this time, I received basically the same. I got 24.71 up to 25.32. Little different. I had 25.31 on the presentation. So we're still doing a test. We still have to report the 5 things if we can report them. So we're still going to have a conclusion or interpretation. And I have that here. Our sample mean is not equal to 24.5. Just kind of refresher, that's what we were testing. We have our null hypothesis is that our sample mean is equal to 24.5. That our sample is just a random sample from a population with a mean of 24.5. Our alternate in this case is that it's not equal to 24.5. So our interpretation is the sample mean is not equal to 24.5. Why? 24.5 is not captured by our confidence interval. It's outside of it, right? Right? It's outside of it. It's lower than that. So that's our conclusion interpretation. Do we have a p-value? No. Do we have a test statistic? No. Do we have degrees of freedom? No. Do we have a test? Yeah, we did bootstrapping. We did a bootstrap confidence interval. So this would be a nice time to give our bootstrap confidence interval to remind the reader. But in some cases, we'll probably say our bootstrapped mean and then give the mean and the bootstrap confidence interval together. And then say it's not equal to 24.5. So the readers can see it. But we have to give some evidence to support our conclusion. With all of our statistical tests, that evidence is our test statistic, degrees of freedom, and p-value. For our bootstrapping, our evidence is the bootstrap confidence interval. How many people had a number that was different than these? Did any of them capture 24.5? I'm gonna guess no. We have a fairly large sample. For pond 1, we have 200 data points. Doing a bootstrap replicate is going to give us pretty good estimation of what our actual mean is from a population. And that mean, yeah, it's different from 24.5. So now what we can do is, so again, it's 100% valid. It works. It's acceptable, but p-value is not so. We don't have a p-value. So let's get to the practice. We've done a t-test. We did a sign test. Let's go through and do our confidence intervals for ponds 2, 3, and 4. and test if our means are equal to these values. Is it working? Yeah. Terribly difficult, hopefully. So pond 2, is it equal? Do my bootstrapping. I just copied and pasted it and updated the pond references and our write-ups and stuff. So you can see the only thing I had to do was update the reference. We're still going to use 95% confidence intervals, but we're still using 10,000 replicates. So here we're asking, is our mean equal to 25.15? 25.15 is captured. It is captured. So it is equal to that. If I'm going to run this a few times, we're kind of right on the edge. So I would run this a few times just to confirm that it does stay in. So I'm going to feel pretty confident that our mean, our confidence interval is capturing it, so we can say that the means are equal. Pond 3, not equal, is it less than, right? 3 and 4 would be one sample test. And technically, if we do this, then we should do our bootstrapping, and we should make sure that all 95% is to one side. But I don't really like that, because we're not really going to get a true 95% confidence interval, right? Our confidence interval would be some value and then it's bounded. It'll go to negative infinity or positive infinity because we're saying we want all 95% of our values to be on one side. That's like the one-tailed test. Typically don't do that. So when it comes down to these one-sided tests, the less than or greater than, what I think is generally acceptable is to go ahead and do a regular confidence interval, 95% confidence interval. It's just like we've been doing. And first see, is our value equal to the hypothesized value? If it's not equal, so if we reject that null hypothesis, then we look at our value and basically make the claim then, well, if it's not equal, then it is greater than that hypothesized value, or it is less than that value. So for pond 3, we ask, is our mean less than 25.05? Well, 25.05 gets captured by our 95% confidence interval. So since it's captured, we conclude that no, it's not less than that. They're actually equal. Our sample mean is equal to 25.05. It's not less. And we report our confidence interval. And then pond 4, we ask, is our mean greater than 23.75? Well, when we do our confidence interval, 23.75 is down here. And we're asking, is our sample mean greater than that? Well, our entire range is higher than that 23.75. So yeah, we'd say our sample mean is not equal to 23.75. And since it's not equal, we know that our sample mean is actually will be larger than that value. All of our values here, this entire interval is greater than that 23.75. So we're not going to really have a lower tail or upper tail when we do these confidence intervals. We still do our regular 95% confidence interval. It just kind of comes down to our conclusions. We can say the same thing with pond 1. So our sample mean. We asked, is our sample mean equal to 24.5? No, our sample mean is not equal to 24.5. Our sample mean, when we look at it, is actually greater than 24.5. And we're going to see it because we've got an option. We've got two options. It's either going to be greater or it's going to be less than. And if we only have those two options and we can show that it's not equal, then we can make that claim, yeah, it's larger than our hypothesized value. In this case, and it's lower, no, our sample mean is greater in both cases. What happens? So none of these are close. All right, none of these are close. What happens if we run it? Let's say we did this one. We've got, this goes up to 25.14. It captures 25.05. And then we say, well, let's run it again. And I run it a second time, and I get 25.00. So the first time, our range captured the hypothesized value. The next time it didn't. What do we do? What should we do? And it's hard to kind of come up with.
Right?
What's that?
Reject, because if it doesn't fall in,
Yeah, but it fell in it one time.
you could run another kind of cut.
Yeah, so now we're dealing into what type of error are we dealing with? Type 1 or type 2 error? Could be both, right? So they're related. So could be a situation where we're just like right on the edge. We're right on the edge. Sometimes we'll reject the null hypothesis. Sometimes we accept the null hypothesis. If that happens, and it's actually in a research project, come talk to me. What I would likely do is I would probably set up a loop, a script that'll redo the bootstrapping like 1,000 times and count up how many times we rejected the hypothesis and how many times we failed to reject. And then it becomes arbitrary and we have to address it. So it's one of those things that if 80% of our randomizations reject the null hypothesis, then chances are we could probably say, yeah, they're different. But if 80% fail to reject it, then it's probably not. And our absolute worst case is we're at that 50%. Sometimes it's in our range, sometimes it's not, and it's random. At that point, it's like we can't tell. We really can't tell if we should reject it or if we should fail to reject it.
You need more data.
Yeah, probably need more data or come up with some alternate method to use. But again, bootstrapping is really powerful. As you're going to see with other randomization tests, it helps us get around a lot of these assumptions. And that's where a lot of the new statistical research is going, is how well did these old tests work? How well do they work? And they're using randomizations to do it, and we're learning that some of these tests, like ANOVA especially, is actually pretty robust. Pretty robust. All right, so I've got this homework where you can assess, you can check your assumptions of a one sample t-test, and then choose to run a sign test or a bootstrapping. But there's a homework assignment that kind of gives you practice, or practice. Just have to find it and get it posted. All right. Moving forward. So we've had one continuous variable. That is what we've been working on. How often is it that we'll have one continuous variable? Depends on what you're doing. Depends on what you're studying. Right. Most cases, when we do an experiment, we're going to have at least two groups. We're going to have a measurement variable. We measure that same variable on both of our groups. And if we have two groups, we can't really run one sample test. We can't calculate the mean of one group and say, well, is the mean of this other group equal to this value, and vice versa, because we're going to start repeating tests on the same data set, and that increases our error rates, increases the chance that we're going to make a mistake. So what we have to do is come up with test options that allow us to run a single test on the entire data set, where this data set has a measurement variable and some sort of categorical or grouping variable. So what we're going to do is move towards ANOVA and t-tests. Both of these tests require one categorical variable. That's going to be our independent variable. And we'll have one quantitative variable, some measurement variable. That's our dependent variable. So with these tests, we're basically asking, is our measurement of this dependent variable, is it actually dependent on which group we belong to? The difference between ANOVA and t-test comes down to how many of these do we have? How many groups do we have in this categorical variable? If it's only two groups, we can run a t-test or ANOVA. If it's three or more, we can only run an ANOVA. All right, so here's the setup for this part. We measured some variable for our different groups. Some variable, that's going to be our dependent variable. That's quantitative in nature. We've measured it. Why is it called a dependent variable? It's because we're determining if this value is determined by our classification. Meaning, does it depend on which group we're in? And this could be more than one. This could be more than one variable. So that this dependent could be dependent on 2 or 3 or 4. And that's kind of what we do in the grad stats course. We kind of take it that next step. What about this different groups? So we measured this variable. We measure the same variable across all groups. Well, what are the different groups? Well, collectively, it represents one variable. It's our classification. That's our one variable type. But that variable is going to have multiple levels inside of it. So if we looked at size against sex, well, we can break up sex to male and female organisms. If we were doing height, let's say That's where you have height. Our sex would be the grouping variable, all right? And that grouping variable has more than one level in it. We call it the independent variable because that's not being affected by any other group. We assume that we've just arbitrarily assigned them, or nature nature assigned it. All right? We had no control over what was produced. This also applies if we do like an experiment in, let's say, the greenhouse, where we use different nutrient conditions, different fertilizer conditions to grow plants. Our independent variable is the nutrients. Did we have control over the nutrients? Yeah, we had control over creating the nutrient conditions, but we basically arbitrarily assigned plants to this group and this group. Being placed in this group really did not affect the probability that a plant would be placed in another group. So that's where our independent variable comes into play. And when we do this type of experiment, when we do this type of experiment, we're asking biological questions that is basically, is the mean of all of our groups the same? Right? That's one of our biological questions that we could ask. Are the means the same? Or we can rephrase that and say, does our independent variable affect the means? Or is our means dependent on our independent variable? They all get at the same approach. Are the means different? Because our null hypothesis for these tests is that all of our means are the same. Why is that? Because we're going to assume that all of our groups come from the same population. If we have one population, this population has a mean and standard deviation. If we take a random sample from this population, each one has a sample mean and a sample standard deviation. Each one has a sample mean, sample standard deviation. Now, as we said, if we have a true random sample, then these approximate our population group. So our approach to this test is to assume that each of our groups just represent a random sample from the population. And if that is true, then our groups are going to be equal to each other, and those would approximate our population level mean. And that would also apply to their variances. So our variance of A, or our standard deviation of A, is equal to the standard deviation, which is equal to the standard deviation of group C, and that approximates our sigma. Our alternate, then, is that at least one X bar differs. All right, so it's either they're equal or we have a difference with at least one. It could be all of the means are different. It could be only one is different. It could be that two. Well, I guess if two are different, then all of them are different, right? Okay. So our approach is to assume that all of our groups come from one population and see if they all come from one population, how likely is it that we'll get our actual mean values just by random chance alone? And that's going to be our p-value. That'll be our p-value. All right, so which test we run comes down to how many groups we have in that independent variable. And you're going to see our independent variable is going to be nominal or ordinal. Our dependent variable is going to be discrete or continuous. So it works with discrete data like Poisson binomial distributions and so forth. Right. So the choice of our test depends on the groups. If we have two groups, then we can run a two-sample t-test or an ANOVA. And you might think, well, hold on, why can you run either one? Well, because an ANOVA is going to generate the same p-value as a two-sample t-test. You can think of a two-sample t-test as kind of being a specialized version of the ANOVA when we have two groups. Our test statistics will be different, but the p-values come up to be the same. I actually prefer running an ANOVA because it's more robust to violations of our normality assumption than the t-test itself. So if we have slight deviations from normality, ANOVA can still work, t-test not so much, especially if our skew's in opposite directions. If we have 3 or more groups, then we are restricted just to the ANOVA itself. All right. So what we're going to do is start with our t-test, which is 2 groups, and I'm going to kind of walk you through like the theory behind it, test statistic and so forth, but then we're going to do all of this in R. And we're going to actually go through the process of checking our assumptions to confirm everything is met. So this part, you can say, oh yeah, it's 2 more tests, we'll be done with it. No, it's actually more than that, because this is going to go on to 1, what happens if we violate the assumptions? What tests can we run? What's our options? And then 2, if we happen to reject our null hypothesis and conclude that at least one means different, then we also have to say, okay, our next question then becomes, which means are different? And that's our post hoc test. So we're going to spend probably the next 2 weeks on ANOVA, possibly the next 3 weeks doing this stuff. Because if we violate the assumptions, our standard post hoc tests no longer work. We have to do alternate post hoc tests. So let's stop here. On Friday, we will start with this t-test, and we'll work on it. All right?
On a test, if you give us, I don't know what a word problem would look like, but it had like the 2 samples in the same population. If we chose to run an ANOVA instead of a t-test, like, would you care?
Where I count off? No.
Yeah.
No. If we have 2 groups and you just say, I'm going to run an ANOVA, that works. That works. ANOVA is robust to violations of the normality assumption, and that's going to be the assumption that we most likely violate. If we have unequal variances, then we could run either a t-test or an ANOVA, because there is an adjustment to the unequal variances, and both of them are actually fairly easy to run. But the ANOVA is a different function to get to that. T-test, yeah, if it's 2 groups and the variances are not equal, I would run a Welch's t-test instead of a Welch's ANOVA. But if we have more than 2 groups, then you can only run a Welch's ANOVA. And good thing you asked, because we're going to learn how to do like randomized ANOVAs and randomized t-tests, and that can apply if we violate all of our assumptions. So I don't want you to think, well, I'm just going to always answer randomized ANOVAs. You'll lose some points if you do that. So I think I had that. I think I updated that on one of the exams to say, don't answer randomized tests for every single one. Because yeah, I had a hard time. I was like, yeah, you can do that. Yeah, you can do that. It's harder. Yeah, we'll pick this up on Friday. Pick this up on Friday, and we'll actually we'll start a new RMD document to work on it. And I believe that we're starting with all of our assumptions are met, and then we'll move to violation of the assumptions. All right.